You have to click something on your computer. Oh yes. Okay.
So, welcome then everybody to this week's Origins Colloquium. It's a pleasure to welcome Ilse Cleves to give the talk this week. And Ilse received her PhD from University of Michigan in 2015. She was then a Hubble Fellow at Harvard Smithsonian for several years before joining the faculty at the University of Virginia, where she is now a tenured associate professor. And she's worked on a whole range of topics related to protoplanetary disks, and we'll hear about some of that today. In particular, she's the PI of the ALMA Large program at DECO. So welcome, Ilse. We look forward to your talk.
Yeah, thank you very much. I hope you can hear me okay. I'll try to point towards what I think are the microphones. There's multiple in this room. Yeah, otherwise, I'm Ilse Cleves. Besides being an associate professor in the Department of Astronomy, I also have a courtesy appointment in the chemistry department, as well as an adjunct appointment at NREO. So I wear a lot of different hats. I also am the one that brought those scooters in. So I'm a bringer of scooters, of toasters, of things. I wear a lot of hats, clearly. Today I'll tell you a bit about where we are with this ongoing ALMA Large program, the Disk-Exoplanet C to Onnection project. I feel like putting a ratio in an acronym in a title. I don't know of another case of this. I feel like we can at least claim that as a first. This title was like the last 24 hours right before submitting this ALMA proposal. What are we going to call this thing? The previous title had been much worse. It was called DIGS, the Disk Gas Survey. But it had an icon of a dog like digging out of a disk, molecules like behind it. So that was pretty cute. Now our logo is pretty cool too. Jupiter and a protoplanetary disk simulation melding. Okay, so this audience doesn't need any motivation after the last few weeks of the KSPA workshop, but just to bring us all onto the same page, we're in this wonderful time where we know a lot about planets outside of our solar system, so-called extrasolar planets, going from the initial discovery to statistics on their orbits, their companionship, etc. Now to a new era of detailed characterization. What are these planets actually made of? And it is clear that planetary systems are highly diverse. Of course, there are systematics that make it challenging to find planets like ours, but on the whole, we're seeing a whole lot of things that don't look like, right, our solar system. But the next frontier of this field comes with a lot of new, exciting, and arguably some of the most challenging questions. We want to know what is the most common outcome of planet formation, small planets close in versus further out. How often do you get a gas giant, Neptune, etc.? What types of orbital architectures are possible? How often do you get compact systems versus giant planets on orbits that are well beyond that of Pluto, for example. So how do these things form? How do they evolve? And what can we learn about our place in this broader picture? And then, of course, the exciting question is, how common is it for a star to possess potentially habitable planets that either may look like Earth or something different? Did we need to actually form around a G-type or originally K-type star? Or could an M dwarf have sufficed? We don't know. So our group takes the angle of looking at the planets before they are formed by studying protoplanetary disks. These are systems that are either have recently formed planets or are currently forming planets or will form planets soon. Depending on who you ask, you'll get a different answer there. But by looking at these types of systems, we can ask or answer some questions. Are, for example, prebiotic ingredients like, for our case, water and organic material, commonly available as basic planets are forming, or are they rare? What kinds of planet masses and orbital architectures are possible? If you have a total mass of your disk that is far less than a Jupiter mass, you're unlikely to be forming a giant planet. If your disk is much larger versus smaller, are you going to form tightly packed systems or something more extended? So what is possible? And then how unique and crucial were the events that led to our existence? For example, the sun was born in a cluster, but we were born in the outskirts of the cluster. What if we've been born in a different part of the cluster, or a cluster of fewer smaller stellar mass content? So how important were the various conditions that led to us? And so how do they influence what the composition of the disk is? I'm kind of a person that moves around, but I'm going to try and stay put. This over here is an actual image of a protoplanetary disk. One of my favorites of light scattering off the surface of a disk, scattering off of those tiny dust grains we all love. The dark plane in the middle that is kind of hard to see at this contrast level is the midplane. And then this little fuzzy halo on the back is the opposite side of the disk with light scattering essentially around the disk back to our line of sight. Beyond dust, there's a number of ways in which we can probe what is going on with the pre-planetary materials. So we have many different wavelengths of light we can use to study disks, but also many different molecules we can use to study disks. So at the sub-millimeter wavelengths now, we've imaged a number of different molecules. Here is just the case of a particularly closed protoplanetary disk, TW Hydra, where the extent of different molecules is radial extent, is different compared to for this carbon monoxide versus its rare isotopologues versus something like CS, which tends to trace denser gas. In the dust, depending on the what wavelength you're observing, you're going to see different physical components. So if you're looking in your ALMA continuum emission, for example, here you see the nice little ring structure that was published now some years ago. That's thermally glowing small dust grains, millimeter-ish in size, sub-millimeter in size. And then here you have the scattered light component. So light scattering off the small dust grains that are elevated on the gaseous disk, extending clearly much further out to the sort of sizes more like what CO is traced. So you see a whole lot of different processes, a lot of different components of the disk, depending on what molecule you're looking at. But that's just one small part of the wavelength spectrum. Even there, to study protoplanetary disks, we draw from wavelengths of facilities that cover the entire wavelength spectrum, from processes like in the X-ray and UV that trace what's happening near these very young, active and accreting stars, to the warm sort of innermost disk in the inner tens of AU out to the sort of far infrared, the innermost disk now with JWST, and now we have ALMA. And thank you, Shazari. Sorry. So I stopped moving around so much. ALMA and VLA, eventually NGVLA and the GBT. And so just to give you a sense of like the quality of data here, we're stepping through velocity space of gas in orbit around, this is a star that's a bit more massive than our sun at the center point here. The star is not visible, so it's orbiting what looks like nothing. There is a star, but you're seeing the cold molecular gas both coming at you. So if you see this little ticker marking up here in kilometers per second, you're seeing the redshifted to blue shifted component rotating through the disk. So, and then if you look carefully, you might pinpoint there's a U-shaped seat of emission here, and then another one on the opposite side, and that's the front side and the back side of the disk. So the data are quite exquisite. We're able to see a substantial amount of detail. So this kind of information is not just cool to look at, but also crucial for trying to build up a physically motivated picture of what's happening within planet-forming environments. So by collecting as much knowledge as you can about your source, that's the star and the disk, you want to build up some physical intuition. I guess I could use the pointer here. So then the people online can see it, yeah. You can build up some physical intuition about the structure and how that affects what we observed. If there's, for example, large inner gas deficit, or a gap in the gas or the dust, you have to assume something about the radiation fields that impinge upon the disk. From this, you can assume how the chemistry is evolving. Sometimes these things are coupled, sometimes they're not. You try to make some predictions for what we would see with a telescope. You want to make a model that's as close to your observations as possible. So sometimes if you're working, for example, with ALMA data, you don't actually get an image off the telescope, you get measurement size, you get visibilities. And so we can compare in that space as well. And then you can do a model data comparison and then start all over when you find that everything doesn't match as you wish. So models can be quite complex. You need a lot of constraints. Ideally, you want to know something about the UV field without having to assume it. But sometimes you can, if you're working with a chemical model, you can go backwards too and infer things like that can't be seen, like cosmic ray ionization rate, one of my favorite parameters. Okay, so together we have this sort of somewhat standard physical picture, which hasn't evolved much in the last, couple of decades. on the whole, we have this decreasing temperature gradient where the innermost disk is hundreds of Kelvin. As you go further out, it drops fairly quickly out to sort of 50 Kelvin, and then to the outermost disk can be something, as cold as 10 Kelvin, sometimes less. The densities are different from what you might be used to if you're looking at the interstellar medium. So the innermost edge of the disk can be as high as sort of even 10 to the 12 to the 13 particles, or mostly H2 per centimeter cubed, dropping out to something like 10 to the 5, 10 to the 6 parts per centimeter cubed, at which point a protoplanetary disk person stops caring, which is like the beginning part for ISM studies. Sorry, ISM studies, but it's just too tenuous for us to even see. So but you get very strong density gradient. So all that's happening, 7 orders of magnitude in density in 100 AU. So it's an extremely strong gradient. But I skipped a few slides for the sake of time here, but just basically the emerging picture from what we've seen from observations of disks in their chemical structure, and I'll unpack this a bit more in the coming slides. But the key difference that's coming out of the last sort of decade of chemical models of the state-of-the-art observations, resolved observations, is that disk chemistry generally behaves like interstellar chemistry, which is good. We can apply like our knowledge of interstellar chemistry to disks, which is great. At least the small molecules. Yeah, I'm sorry, large molecules are just hard to see.
We're getting there.
We're getting there, yes. But a really key, and I think fun, but also complicated difference is that you can't assume gas and dust are coupled. The dust is, at these densities, it grows so quickly, it can grow to sizes that allow it to dynamically decouple and start to settle out to the midplane. The midplane being the sort of geometrical center of the disk, but then also start to feel a headwind against the pressure-supported gas that is orbiting slightly slower than the Keplerian orbiting dust grains. And so that gives it a headwind that results in it losing a bit of angular momentum, and it starts to drift inward. This is a process called radial drift. We heard about it from Andrew in the first week of the conference, but this is chemically one of the most important things that we've discovered in the last sort of decade that we can no longer neglect safely, which is exciting, but also complicated. So now disks are quite dynamical systems. And that isn't even yet talking about like dynamics of the gas, turbulent motions of the gas, for example, which folks are trying to constrain as well. They generally seem to be quite low. Most of the evolution, the dynamical evolution, seems to be dominated by dust growth, i.e. the first step of forming a planet itself. So yeah, so basically the first step of forming a planet is changing the composition of the planet forming disk. While at the same time, you have planets themselves forming, shaping, sculpting, especially if they're giant planets, carving gaps, which itself can change the composition of the disk by allowing more light to sort of penetrate into the disk itself. So it's a fascinating, challenging problem. And to solve this problem, we have all these different molecules I brought up earlier, and all these different continuum measurements that I brought up are dust-related measurements, because we have both the scattered light too. So we have all these different windows, and you might notice something immediately. So the gas we're tracing is mostly from up here. Why is that? For 2 reasons. Excitation, it's warmer. The gas is emissions dominating the surface, but also sometimes these molecules freeze out. Formaldehyde, CS, HCN, they all have like intermediate binding energy. So below 60 Kelvin, they're ice. That's a rough number there. They all have their own specific binding energies. But you get the point. Basically, we have the zone of freeze out and pore excitation, which is also the planet forming zone. And over here, if we want to learn something about the volatile composition, for protoplanetary disks, we need absorption studies. And I talked about that in the KSP workshop, talking a bit more. I won't talk about that much more here. But this is both a challenge, but also a good challenge, right? Like it's a motivating challenge, because that means we do need to learn something about the midplane. And from all this information we have on the surface, it means we do need models. Models are critical to sort of uncover the unseen component of disks. So over the last few years, this one's a bit of an older picture, but I like it because it includes the laboratory group who you all got, or at least the KSPA people got to meet a few weeks ago, 2 weeks ago, last week? Was that last? No, 2 weeks. It was last week. God, no way. It was last week, Brandon. Anyway, you got to meet them sometime in the past. Yeah, so, and actually today Camille is defending his thesis at 1 o'clock that is in, it's going to be in the chemistry department, I think. I have to find out. I'm on that committee. Read the thesis. I did my part. But yeah, so the laboratory group and our group here, more recently we did an outing for at a local art bar. Crafting as a group. So why am I showing this? Because we have a number of folks that are working on the theory, the multi-wavelength observations, the laboratory astrochemistry side, and now we're bringing in data science expertise as well. Okay, so in this talk, which I have like 12 more minutes at most, maybe, I don't know, to cover, is I want to motivate how we're approaching these problems through the ALMA DECO survey. And if I have time, I'll show you a little bit of fun from James Webb. Okay, so why DECO? Why this ratio C to O in our title? So one of the exciting frontiers in disk chemistry studies is trying to actually link up compositions in planet-forming disks with the actual compositions of planets. I just included Titan because Titan's cool. We're not actually connecting to Titan, but it's pretty. But we are trying to basically model sort of this side. The field wants to figure out what is the detailed disk chemistry, what is the bulk carbon and oxygen content of a protoplanetary disk, and predict what types of planets might form. Simultaneously, the community of folks working on the compositions of exoplanets themselves are going the opposite direction, and they're saying, I have this much oxygen, therefore I formed at this position relative to the snow line. And there's not actually a ton of communication between these two communities. Arthur's nodding in the back, so I feel vindicated right now. But at this point, we're kind of stuck until we have like a predictive model of planet formation. It's going to be really challenging to do a whole lot more. So for now, we're trying to sort of figure out how can we do this better for more disks to start to match up to the statistics of planets, which are also growing in time, compositions of planets. Now, carbon to oxygen is one of the long-standing values or atmospheric properties relating to planet composition that have been found to be at least I was going to say reliably measurable, just measurable. There's variation depending on which model, who you're talking to. That's also true for disks, but it's at least something that affects the spectrum we see in measurable ways that hopefully eventually become predictive. A few years ago now, 2011, Karin had this nice paper showing that under the most basic conditions, no interstellar chemistry, no drifting moving dust grains, you should get a gradient in the carbon to oxygen ratio naturally from an interstellar chemical composition that just is getting colder as you get further from the star. You cross the water snow line, oxygen in the ice, so the C to O ratio in the gas shoots up. And as you cross subsequent snow lines, you get shifts in the balance of carbon versus oxygen in the gas versus the ice. And this was exciting. The exoplanet folks, I think, read this. Most of them just read this paper and quit because it was nice. And Arthur's again nodding here. A lot has happened since then, but you get the idea. It was a nice picture, and it was a way in which if you measure a C to O ratio, for example, of 1, the planet may have formed out here, not in here. Right? So in more recent years, we've discovered that we can reliably measure carbon to oxygen ratios in protoplanetary disks through the use of molecules that trace abundant carbon relative to oxygen conditions. So these are small hydrocarbons, easily observable. The primary workhorse is CCH, also C3H2. These are reliably measurable. This image is a 500 sigma detection of CCH. Because we didn't think it would be that bright. So we integrated for like maybe 40 minutes. I don't know. It was like not even that much ALMA time, but it's an absurdly bright donut. And then with models, found out that by varying the carbon to oxygen ratio, you can get that very bright donut by tiny shifts. Factors of a few in carbon to oxygen ratio would give you orders of magnitude change in that column density. So that was a natural way where we could kind of invert the problem and use this as a probe of the underlying bulk carbon oxygen ratio in the gas. And luckily, this is part of that legacy of interstellar chemical knowledge, because this is a very well-studied system, actually from the evolved star literature, then the ISM literature, rediscovered by the protoplanetary people as useful. And so basically all the reactions, if you have an oxygen-poor environment, lead to C2H formation. You can start off with atomic carbon or ionized carbon. It doesn't matter. You'll get to high hydrocarbon abundances. And the way you quit it, you quit it, you stop it, it's early for me, is by throwing in some oxygen that will immediately form CO. It's pretty simple, it's nice. Okay, so data has stacked up over the years. Here, let me just there. And so if you cross compare what we have from disks, those are the solid lines here in their carbon to oxygen ratio. Ignore the bar because a lot of these were unresolved measurements. They kind of give you a rough idea of what scale CETA was measured on, but there's some iffy wiggle room there. And then if you compare them to directly imaged planets down here, most of those are from HR 8799, exoplanet people, we get a difference. The disks are up here, the planets are down here. They do not seem to look like disks. Planets don't look like disks, so that's bad. A bad thing to see. Caveat, these are a lot of massive planets. They probably formed not by accretion-driven processes, probably gravitational instability, which scrambles up your carbon to oxygen ratio back to stellar values. So maybe it's not a problem. So what other planet data do we have? Transiting data. So I couldn't make this plot in time before this talk. I've shown this plot in front of exoplanet enthusiasts, and they said all of these values up here have been revised down to here. So I just grayed them out for you. Ignore these ones. They were all like Spitzer JWST combo measurements that have now with JWST been moved down into this zone of 0.5 to 1. Caveat there. But main takeaway here is they're still kind of down here. Some are 1, some are 0.5, but disks are still generally quite high. So, okay, these planets might have some more elevated values. They maybe look a little bit more like the outer disk. So maybe you have some migration effects. Maybe if they formed in systems like calcium-15 or ion loop in the outer disk, maybe they all just migrated inward, carrying their composition of the outer disk inward, nothing to do with snow lines. Or, well, they could be just this sample of disks is potentially just not the right sample. They're not the planet forming sample. These are generally the first disks studied are often the biggest, most massive, and most biased. And so this was the question that led to, in the last 5 minutes, the DECO program. So we asked for 150 hours initially to survey 80 protoplanetary disks and carbon, oxygen, and nitrogen tracers to try and build a predictive framework of like, what is an actual chemical structure of a disk to let people who are doing planet population synthesis have a realistic framework to draw from rather than snow lines. We have moderate resolution and a wonderful team of co-PIs. We're using 2 measures of carbon to hydrogen, carbon to oxygen. This particular ratio here and the C2H to CO ratio is what we'll use in practice. But the takeaway again is we have sort of very nice tracers of what I called metallicity in the proposal, trying to reach out to different communities, carbon to hydrogen, but using these 3 lines to basically get C to O, C to H, and then O to H by inference. Now you might wonder, okay, these are all based on models. How do you trust these things? Well, we have a modeling team that's been working for the last 2 years to compare across 8 codes in the literature that model disks that have thermochemistry and God knows what, chemical, like large chemical networks with organics and some with like barely forming N2. So they generally all agree, which is exciting, but I don't have time to share the modeling systematic approach, but chat with me after. We span 4 different regions: Ophiuchus, Lupus, Chameleon, and Taurus, all part of the local bubble. We go down to a Neptune mass disk, so we can form things, planetary systems that don't have a Jupiter. We've split the sample into 20 disks per region. Half of our disks are sort of smaller than the solar system was at its birth, 80 AU, and half of our disks are bigger than that. And to do this science, we needed 3 spectral settings with ALMA, so a massive amount of data, 5 million channels. But with that, we get a ton of bonus science. We'll have D to H ratios, at least limits when we don't detect it. Small organics were detected commonly. We have sulfur tracers. We'll test stellar evolutionary models by doing Keplerian derived masses of our central stars, which will be cool, and more. I'm going to skip our methods. Going to skip match filtering to give you this. Okay, so yeah, so this is 66 of the 80 sources that fit on my slide. They look like little cute blips, and that is because they are small. Some of them are, most are resolved actually, we discovered through fitting the visibilities and the continuum visibilities, but some are not resolved, but they're all generally quite small here. And so that is good because we're trying to find analogs to our solar system, not to like the giant ion loop disk that I showed you at the very, very, very beginning. And so each of these had 3 spectral settings, each with 12 to 13 spectral windows. Not always just emission, we see a whole lot of structure as well, not just Keplerian rotation. And so we're going to provide all of this back to the community via a giant, we're aiming to have a big data release. And we also more recently in the last couple of weeks also put out our CO, we have our CO maps. And so we detect CO in all of our disks. Some of them have more structure around them and some look like cleaner. And if you look carefully, you might notice Rho-Ophiuchus is more structure than the others, and that is because it is youngest. I'm going to skip our modeling stuff. Our lovely team. We are over 60 people now. We span 4 continents, 8 countries, and maybe more countries now, 7 time zones. It does make telecons really a nightmare to schedule, but we're trying. And half of our team is either postdocs or students. And they were here where we took our picture for the workshop in May of 24. Okay, so what do we actually see? So I will show you a couple images here besides the CO, but here are the spectra. I think the spectra show nicely the diversity. Each of these is a line. So CO, 13CO, CH, CS, C2H, HCN, formaldehyde, N2H+. And then across, the colors are single disks. So sometimes you have disks where you don't detect CO, but you detect hydrocarbons. So those are interesting. Sometimes you see really strong CS, but really weak N2H+. CS is a dense gas tracer. And if the N2H+ is not showing up, why is that? Interestingly, while our beam is between 0.2 to 0.5 arc seconds, which is, we're talking about like 40 to 100 AU, 100 AU is our common beam, we can still super resolve by looking at the velocity, the high velocity wings, which trace gas orbiting closer and closer and closer to the star. So we can reach sort of 10 AU scales by knowing the inclination of the disk and the stellar mass. So you can infer like what's happening in the innermost disk without directly imaging it using the wings. So that's pretty cool. One of our initial findings is that the hydrocarbons, the C2H, is seen in most of the disks, but only a quarter of our younger disks, roughly. And this is not unexpected, perhaps. It's interesting. We're going to confirm why it is. But if you take a simple picture of a disk that has yet to undergo a huge amount of settling and growth, the gas and the dust are well mixed. Oxygen is everywhere, hanging out at all positions. So your carbon to oxygen ratio in the bulk is closer to the stellar value of 0.5. But as you grow dust grains, typically you sequester oxygen-rich ice like water and CO2. And if those tiny icy grains take that ice, settle it out, and send it to the innermost disk, you are left with a carbon gas-rich outer disk environment. And so we do expect this to increase in time. Another possible explanation is that the younger disks, so these will be results by Ashish Gupta. So the younger disks have a lot of interesting structure around them. We see, these are not ALMA artifacts. We see like hatching. I don't know what it is. It's very strange looking. Some people like look at it and say magnetic fields. I don't know, but a lot of it's bound, actually. That's what Ashish has estimated. It's bound stuff. And so another explanation could be carbon to oxygen ratio defaults to being high, even for the young disks, but late stage infall tends to bring in pristine interstellar gas, which tends to have a carbon to oxygen ratio that's lower. So it could be late infall. Here's a case where the late infall is like beautifully like imaged. So here, this is the rotating disk, the donut. It's not a binary, you're just seeing the red and blue shifted emission. This, I think, is a moment 8, the peak intensity map, but we see this arc coming in CO, 13CO, the HCN, but multiple hyperfine components here, and you can see maybe there in the rotation, the moment 1 maps. And we also see some kind of funny things that look like proplyds, but in regions that are not massive star occupied. So here, there's some nearby B stars that are kind of far away, but this disk happens to be moving in this direction. So is it like a wind plowing through ISM? I don't know. So that's a lot of bonus fun science. I don't think I had time to go into JWST side of things, Jonathan, right? I need to conclude now, so I'm gonna.
Well, if you want to take a couple more minutes, it's fine. You know, we're flexible.
Okay. The ALMA results I've shown you so far are on at best 10 AU scales, if not much larger scales. So what about the actual terrestrial planet forming region, sort of 5 AU-ish scales? You have to understand the full ecosystem to actually understand what's going on those terrestrial planet forming scales, because like I said, it's all coupled. You have dust growth transporting volatiles between the outer disk and the inner disk. So as predicted, so Dana is now faculty at the Naval Academy. Hooray, Dana. She was a DECO postdoc here a few years ago. But while she was here, she did this a nice study. I won't go into the details, but the takeaway point here is that regardless of what she threw into her disk model for carbon or oxygen carriers, she wanted to know if you could see carbon grains getting destroyed in the innermost disk. But if she threw in methanol or carbon grains, she got the same answer. It just depended on the carbon to oxygen ratio that was in the bulk gas, because everything's destroyed at an AU distance. But then we turn that around. Hey, that means the inner disk composition is actually a really good tracer, not of history, but of carbon to oxygen ratio. So that came back to this exciting story. So a couple of different models had predicted out there, theoretical models had predicted that your carbon to oxygen ratio in your outer disk versus your inner disk will be different under different underlying assumptions. This one's just cooking chemistry in situ. Don't move your dust around. Here is unabated water drifting inward to the central star, so you get a lot of oxygen. Or if you starve it by throwing a gap in there, like a hard trap, raise the carbon to oxygen ratio by preventing water from reaching it. So there's a lot of different predictions. We wanted to figure out which one made sense. So we asked for JWST time. We got it. It was exciting. We called it Interdisk Deco, or iDeco for short. This was 40 disks. Now we'll get another 20 this coming year. So we'll have 60 of our disks with JWST. The data quality are beautiful. This is one published example from Sierra Grant from the Mines team, not DECO, but this same data quality is what we're getting with DECO. And as you can see here, it looks like noise. These are lines, mostly of water. But here it was so sensitive that they got not only 13 CO2, or 12 CO2, they got 13 CO2. So to deal with all this data, we have a specific JWST hack team shown here, doing a number of different projects with the data, including dust mineralogy in the silicate feature, but looking specifically at composition is one of our key goals. And so using a similar relationship, in this case, it's a hydrocarbon to an oxygen-bearing molecule, we find a similar C to O dependence on this flux ratio that, again, factors of a few span orders of magnitude in this flux ratio. It's a very nice handle. And so for our data here, so this is outer disk from ALMA in the literature. The original figure I showed you in orange. The transiting planets blanked out with those high ones that apparently are untrustworthy. We get values down here for the old disks and then the young disks here in orange. And they do span 0.5 to 1. They're not following the sort of Oberg drop of down to 0.5. They are elevated. We do have some upper limits, but on the whole, we see mostly detections here. And so that, if that ends up holding, we're again doing a lot of modeling, that could even prove that giant planets don't have to migrate to explain high carbon to oxygen ratios. TBD, of course. We're not saying there's enough mass or the mechanics work, but we're saying the composition is not a unique marker of migration. So yeah, so we put together this really complicated picture trying to explain the evolution of carbon to oxygen ratio for our JWST proposal to look at young disks, inner disk carbon to oxygen ratio. We think that the youngest disks might have this sort of, start off with this initial 0.5 C to O ratio before a whole lot of drift happens. Once you have, let's see, some large influx of water-rich ice, that will creates lower interdisk C to O ratio. When the hydrocarbons come in, it elevates C to O ratio. And then later you could have some late stage infall of low CDO ratio gas. We're trying to figure out why this time dependence is happening, why you end up with a high CDO ratio and a low CDO ratio. We're gonna get a sample of 20 disks in the next cycle. Okay, so is this now impossible? Like I told you, models are really important at the beginning. They were already multifaceted, and now we know that there's like dynamics happen and maybe infall is happening. Most of the time we have to model each of these things separately. But I'm optimistic that because we have now active facilities for at least a few of these and working on the far infrared here, we have probes of all these different physical components to assemble sort of a comprehensive chemical evolutionary model of planet formation. Okay, so sorry to go a little bit over, but my summary essentially is planet formation is a complex process, both physically and chemically, but our data are improving exponentially, and models are getting there too. Data are ahead of models, at least for now. Disk studies are really benefiting from both having these in-depth studies of source-specific projects, but the statistics from the samples are going to put this into context, into really showing us what are the dominant processes. Having better physical and chemical models is essential if we're going to do planet population synthesis to try and explain the planet population out there. We need good models to actually synthesize from. And so trying to base this on data is where we're going with DECO. And yeah, and so doing this is also important because when we're going out and looking for biosignatures on planets using hundreds or thousands of hours of time on major telescopes around M dwarfs, we need to make sure those are worthwhile targets. So yeah, all right, that's all I have. Oh, thank you. Yeah.
Great, thank you very much. So we have time for questions and the discussion. Maybe we can structure a little bit. At least in my mind, there's two aspects. One is what are the systematics in trying to measure things like C2O, and how certain are we of the measurements, and then the kind of correlations you're finding in different systems. So maybe we can start with the systematics.
Yes. I'm looking at my slides to see first on the systematics question if I have it on this slide deck. I don't think I do, unfortunately. But across. Go ahead.
Yeah, I was just going to say, for example, I mean, the molecules are coming from different places in the disk, are they? Different layers, and so when you measure a C2O ratio, it's all backed out by comparing to a model. So what if you change the aspect ratio of the disk or the FUV luminosity a little bit, or how sensitive would the results be?
That's a great question. It is the slide I skipped. So Amina Diop, a graduate student here, finest fellow, yay, is, let's see, oh, can I find you, Amina, doing the cross comparison of the modeling. Yeah, okay. So so in terms of the systematics, we have two efforts. So Dana Anderson is leading the cross-code comparison of 8 different codes to see how a different chemical network affects our ability to actually measure or extract C/O ratio. What we do see is there are differences between codes because everyone has written a code to either model a Herbig systems, thermochemistry, or measure or try to predict complex organics, or try to do thermochemistry without worrying too much about things like N2H+. I'm not naming codes here, but like codes were all developed for very different use cases. The code we use focuses on the ultraviolet, the ultraviolet and X-ray radiation fields and how they go through the disk in a wavelength dependent fashion. So we focused a lot on radiation transfer more than others. And so every code has a specialty area, but what has held is that every single one has the same trend in terms of sensitivity. Like they vary by the same factor in C/O ratio or line flux versus C/O ratio. So the general overall profile is the same across codes, but the absolute value will be different because every code has slightly different C/O predictions for their own code base based on what they've assumed. But we will be able to, in a relative sense, say like which disks are high C/O, which disks are low C/O. We may not be able to exactly tell you C/O ratio to 10%. Nobody can do that. Don't trust them if they say they can. For the systematic, the second part of your question, which is like dependence on the flaring angle or the ultraviolet radiation, you assume that's Amina's project. And so Amina has almost 90,000 models that are going on Ravana, and I'm sorry to all Ravana users, but we're trying to, yeah, I know. We're trying to break through all barriers of model limits right now. But yeah, so some of the disks we have, we'll measure the CO sizes. So we have that as a way to break degeneracies. We know the stellar masses. Over 70% of our stars have known X-ray fluxes already in the literature, which is great. I wish it were the rest, but Chandra did not say yes to us, sadly. But yeah, we're trying our best to limit unknowns, but we're allowing in our MC approach, allowing for, we have variety of opening angles, critical radii for the parameters we don't know.
Mhm.
And then for do the trends hold in both the LTE and the non-LTE regime for both the ALMA observations? More likely that there than with the JWST observations.
No, that's a very good question. So we are assuming we're running Lime models for all of, or measuring everything from our full 2D models, making radiation transfer simulations, getting line fluxes, which comes back to your original question, Jonathan, about like emitting regions. That's all folded into the model. Like we don't enforce C2H to come from the same gas as CO, for example. It's wherever it wants to come from a model. But yeah, we are assuming LTE at the moment for our radiation transfer because it's just for speed. 90,000. Actually, no, it's more than that because we need to predict 4 different lines. So that'll be like 270,000 lines.
And do you have a chance then to resolve the C-to-O ratio so you could measure it in the outer disk versus the inner disk from the ALMA data?
The ALMA versus the JWST data.
No, well, no, just from the ALMA alone.
Yeah.
Could you do that?
Yeah. So I was getting to that. We had to basically, it took 22 months to take this data with just ALMA. And so some of our beams for Taurus are humongous. I'm sorry, Taurus people, but Rho-Ophiuchus has like beautiful 0.2 arcsecond beams in some cases, which is also kind of a bummer because they're the ones with structure. So we're actually less sensitive to that large structure. The fact that we see so much structure is telling you there's a lot of structure in Rho-Ophiuchus. So maybe for some of the cases, but not all of the cases, we have resolution. That is not a priority paper at the moment. We do have, so Charles Law will be doing like the radial size analysis, looking at like are CS sections always compact or extended, like in a statistical way. But yeah, we're not doing C-to-O in a resolve sense yet, but we will make all of this public for anyone who wants to do that.
Great. Any other questions on systematics before we sort of go ahead and trust your results and ask about the
you don't have to trust my results. That's the fun part.
So then any questions in general about the results that are shown?
Go to the C-to-O ratio plot if that's inspiring, or the maps. The structure with the hatching. Oh, those maps, Ashisha's maps. Yes. Yeah, I don't know. The scale is. Oh, that's a 500. I think that's 100 AU. Yeah, that's wrong. This is an old plot. Those are 100 AU bars. Our disks are not that big. Yeah. So I don't have the names here. I know some of them off the top of my head, but not all of them. Yeah. So we see hatching. So where's the disk in that one? Oh, they're all in the center, and so in this case, center, and then you have this extended. Yeah, example where there's like, you can see the disk. Oh, wow. And there's the disk. And this is like extended structure. I don't have the slides, but so Ashish is looking at how much of the gas is bound by taking its velocity and taking its projected distance and then assuming either the projected distance is the actual distance or assuming some like intermediate, like half of it's in the projected direction and half of it's in the plane of the sky. And so he has a couple of different estimates for the fraction of bound gas. And the majority of Rho-Ophiuchus disks have, I don't have the slide in here, unfortunately, but the majority of disks in here in Rho-Ophiuchus have bound gas. So I don't know, he has it all marked off on graphics that show like which features are bound and which features are not bound. But yeah, so he's done that estimate. And then Lupus has the least amount of bound gas. I think it was like less than 10% from Lupus. And then Chameleon and Taurus were intermediate. And some of them are known, like DR Tau has known like infalling streamers and such like that. So I'm not surprised that Taurus has some more bound gas. Yeah.
I had a question about the C to O ratio. If you bring a lot of water in, you should drive the C to O ratio down below the 0.5 level, but I don't think I saw any data in that regime. Is that a surprise to you at all? Or?
It was a limit. It's an observational limit. I don't think we can. We'll try. We're going to try to see where the models can get down to, but so you need to detect the hydrocarbon. So if you don't detect the hydrocarbon, but you detect the oxygen carrier, that's an upper limit. And if you detect the opposite, you get a lower limit. And so that's just
the triangles are upper limits, are they?
Yeah, the triangles are upper limits. It's not that they don't exist. We just don't have any. But I think it's more surprising, at least to me, that most were detected and they are not below 0.5. So this is just the Rhoophaeacus ones that were observed in the archive. We'll get the additional, I think there were 7 total observed in the archive. We didn't have access to all the data at the time, but we'll get the 13 more orange points to fill this in to see if there is in the young disks a giant influx of oxygen. But again, I think we are going to still be limited at 0.5 probably.
Great. Any other questions? So Shazreen, yeah, please, Shazreen, help moderate that then.
Maybe Mika go first and
then. My question is a little more ahead. Maybe when you analyze the JWST data, you may get more answer. But when the chemistry of, CO ratio is changing because the ice is formed and then these ice take all of the oxygen. But how much of the ice, how much of the oxygen has been taken into the ice so far from measurements from JWST?
Yeah, there's only one measurement, the one I showed at the end of my talk from Jenny Bergner's analysis. It was either earlier this year or later last year, where for an edge-on disk, they measured a carbon to oxygen ratio of like 0.2, down at well below the ice values here. I'm going to go back to the slide. So, no, too far there. So they got things in the 0.1 to 0.2 range down here. And the dash line is, they called it grain. That's the ice phase C to O ratio. And then the gas phase, that's the solid line. And so I think that it's going in the right direction, whether like as a bulk accounting, like on a per radius basis. I don't know if we recover all the oxygen. If we don't, I'm not too worried because again, drift is going to like move things in. And if viscous evolution like pushes some of our ice outward, things will move. Things are going to move. So I'm not too worried, but in terms of bulk accounting, we still have to figure out if it is ending up in the interdisk, for example, with JWST. Yeah.
Yeah, about the hatchings, I was wondering, what's the hatching? Yeah. How did they manage to create those images? Because if I remember the talk from a few days ago and last week.
Can you repeat the question? We couldn't quite hear that.
Oh, yeah, I'll repeat it. Go ahead.
They said that they need to assume a disk model and from there try to match the sparse sampling of the Fourier plane. Then they go from ALMA. And so that sort of forces you to have cylindrical symmetry. Whereas here you have straight lines. So that's how you figure that.
So this talk, so I wasn't there for this talk, I don't think. So I don't remember, I don't know the details there. But here I can just tell you what we did. The question was about hatching and how our process of imaging the data would influence our ability to see the hatching. Kind of, okay, so with this data, we did the simplest thing we could because imaging all the lines took many months, and so we went just a straight clean. We just use clean within CASA, and so in that case we assume for a standard clean point sources. So obviously not everything here is a point source. There's distributed things, there's hatchy things, but using standard clean, you basically reconstruct your image plane with point sources and iterate until you have 3 sigma noise. I think it's what we went with in the end is our threshold cutoff. So we don't bias ourselves to any structures to start with. We have no implicit assumption besides the fact that everything can be constructed in point sources. Interferometry, if you have space it, if your antenna array is not ideally spaced, where you might have more coverage in a particular direction and sparser coverage in a different direction, you can end up with artifacts that look like striping in your data. And so the first thing I saw, when I saw this, I'm like, oh, so much we have. Probably the spacing was bad. They were taking data continuously. So who knows, like it's an artifact. But then when we put together the moment maps and saw that it was crossing each other, that is not what you expect to get from weird antenna coverage. And so ALMA is not trying to give us weird antenna coverage, just to clarify. It just, as they go from configuration to configuration, they try to go to an ideal configuration, and then they move antennas slowly to get to the next configuration. And so they'll continuously take data throughout. And sometimes they end up with data that is not ideally spaced, or if you're trying to combine data from multiple coverage, like compact configuration and extended configuration, you might not have like great spacing between them. The coverage might be bad.
So the summary is, you think this is all real, right?
Yes, I think it's all real, but we probably, because the beam is that little dot in the corner is the beam. And so I think we are missing short spacing. So we are not recovering all the flux. So there's probably more unseen structure, or it's more prevalent. Like it might be just more distributed. So it might be enhancing how it looks, but it's there. It is real.
Yeah. Maybe we can go to Lee's question next.
This hatching thing looks very strikingly similar to Sam's JWST observation of the galactic center.
Yes.
HSC. So, and Sam claims that that's actually a magnetic phenomena. So I actually want to ask whether or not you see this only at one. I assume this is the 12 CO, right?
Yes, this is 12 CO.
Did you see that in other molecules or transitions or?
13 CO shows structure. I wish Ashish were here. We were just on a call for the DECO this morning. So that's probably where he is now. But 13 CO, 18 CO, and it's sometimes the same, but sometimes different because of optical depth effects. So sometimes we see a streamer we're calling them kind of streamers. We don't know. We're not defining that in some particular way here. But like sometimes we'll see a 12 CO streamer oriented in a different way than a 13 CO streamer, because we're probably seeing different gas coming into the system at different actual depths as optical depth, as the optical depth effects impact what we see. Yeah. And sometimes we see, like I showed you in this following image here, where it's usually just CO, but we do have cases of extended HCN in this case. And HCN is generally a fairly dense gas tracer, which is weird.
Mm-hmm.
Yeah.
Can you measure turbulence in the disks with this data, or is it not designed for that?
It wasn't designed. We have the spectral resolution, but we don't have the depth of the turbulence measurements that typically required a few hours on source. We were like 20 to 30 minutes on source. We will be able to like say how much non-Keplerian emission there is versus Keplerian emission though.
Mm-hmm. Mm-hmm. And you can see the dust being concentrated to different levels from the continuum versus the extent of CO. Is that coming out of your sample as well?
Yeah, so Luigi Zaldio, and the week that he was during last week, I'm gonna quit saying like last month. Yeah, so he is working on fitting the CO gas sizes in the visibility plane using the tool he developed with Sean Andrews. He collaborated with Sean Andrews to develop called Sea Salt. And so we're measuring the CO sizes. We're in the visibilities. We're measuring the dust sizes. Karina and Malco is doing that in the continuum. And we're also getting some dust morphologies. We have some transition disks. We had sneaky binaries. We tried to avoid binaries, and there's like too many binaries. I can't remember. 15% of Taurus is binaries. Stop. I wanted them all gone. But they got in there. But yeah, so.
So is there any evolutionary sequence of greater concentration of dust would correlate with, I don't know, C-to-O ratio or anything else?
That's what we want. That's the dream. That is totally the dream. So data collection ended in November of last year for a cycle 9 program. That is so long. And then we sadly lost like a lot of our data due to a disk failure. Our storage space is like 50 terabytes. So we lost from February through like 2 weeks ago. And so everything was restored. It was a monumental, but we survived a lot of things. We survived the ALMA hack. That was when this whole thing started. So DECO is fine. We're going to be fine. It just is a slow going process. We are aiming to have all those things done to look for evolutionary sequences. Row of Ficus is our one young benchmark then Chameleon, Taurus, Lupus are kind of the same age. But we
Mhm.
did get approved time in a previous ALMA cycle for upper SCO with the same exact tracers. They're not exactly the same stellar masses, but we will also have upper SCO too. So we will be able to test theories of, is the disk getting more compact in time as predicted by theories of wind-driven disk evolution versus viscous spreading where the disk gets bigger over time. And at least some plots I saw this morning suggested the compact scenario that AgePro also found looks more consistent with the data that exists right now. But that is that's like this more than preliminary, so.
Great. So we're approaching the hour, but any last questions in here or Virginia or online?
Combine me. Yeah, go ahead.
I want to ask more about the C-to-O ratio
Yeah.
connecting to exoplanets. So on the plot you're showing, the far
The
out
final ones? Or this one? Or no,
No,
the
no,
one
the-
from the CETO ratios. Okay,
Yeah.
yeah, go ahead.
So the far out measurements, are they all young disks? Or I don't know enough.
These are all young-ish disks, couple million years old. Rhoophaeus is not appearing in this plot. I can show you offline in a non-recorded setting. We do have our DECO values approximately, or if you were at the Gordon conference, you saw my initial results. But we cover the same spread with DECO. That's what I will say here. And they are even, there is a difference in the CETO ratio for the younger disks versus the older disks. Younger being Rhoophaeus and older being the rest. Not upper scope. Yeah.
So these lowest points on the transiting planets where you're basically at like solar CETO ratios.
Yeah.
These are like pretty much all at the lower limits of anything that you measure, right? They don't match these outer disks. They don't match these inner disks.
Maybe the upper limits. Yeah.
Yeah.
I mean, but if that ends up holding for the full DECO sample, that would say that these planets could not have formed at 10 AU or beyond.
But okay.
They would
So
have
they
to be
would have
more
to be
here.
from into this population.
Exactly.
Your planets are all hot Jupiters, are they? Or are there any sub-Neptunes there?
These are, I actually have a different mass plot, but it's going to have all the systematic funness. Okay, so again, caveat, block out everything up here at the top. This is Keelan Hawk's paper that includes the Spitzer HST ones that are too high. But there, at least from this paper, there was a claim that there's a difference in the carbon to oxygen ratio of small planets with a split of 4 Jupiter masses versus the extended planets that are all sort of 4 Jupiter masses and higher. Now, if those are all eliminated, this is going to be a weaker split, but maybe still there. Who knows? It has to be redone. But yeah, so that's basically the transiting planets are our best sample right now of a diverse number of planets at masses that could have formed by probably core accretion. These probably all formed by gravitational instability, scrambled the ice, the gas, didn't matter, CETO was erased. So they all look like stars.
Mm-hmm.
I
Great
like this
then.
plot, but
Yeah.
it has caveats. Yeah, go ahead, John.
Well, no, I was just, any last urgent questions before we close the session? This was a really great overview of different aspects here. So if not, let's thank Ilse again for a great talk and discussion.